Okay, we're going to get started on this 24th day of April. Constant reminder, where are we? We're nearing the end, right? So we're on the 24th. Just get the calendar set right here. Next week is the last regular week of classes. I guess senior seminar presentations are on this Friday. Senior design presentations are on the following Friday. We wrap around into finals week. The project is going to be due on, well, let me back up. The last homework problems that I posted last Thursday on the 19th, those are due on the 3rd. Don't be confused. They're not due, nothing's due this Thursday. You're just coming in to take an exam. I had somebody write to me yesterday saying they wanted to bring the problems in. They're easy problems. Some of you probably have them done or you will have them done shortly, but I'm trying to separate the exam, which we pushed off to the last possible date, from the last material that wraps up the chapter. So don't get caught up in this is the end of the semester on Thursday, because it's not. We're just taking the last exam. But at any rate, on the 9th is when I've got the project due, and then on the 10th is when you come in to take the final. And the final is at a different time. It's like whatever I said last week or looked up. I wrote it on a document. I wrote it on the project, actually. Yeah, 12:40 to 1 or 2, yeah, 2:40. Yeah, it's exactly 2 hours. So just keep that in mind. That's probably one of the most important things to be doing as a result of what I'm talking about, is do something to your calendar to remind yourself that the final on the 10th is not at this time. I've been teaching this class at this time for many a year now, and I feel bad when people walk into the final late because they're thinking they have to be here at 3:05. I remember one time I actually had some students who were studying in the library, and they mysteriously didn't show up here, and I had the email handy, so I sent them an email message, and they came running over because they had forgotten the time was different. So, okay, I've posted a TBD written version of project number 2. The first part of it is very similar to what it has been, so that is reposted properly but converted to work with the scikit Python package. I've added in a bunch of the content for the second part because I've written new code, which eventually will get pushed in up to GitHub, but right now it's embedded in the notebook. So we'll get a chance to look at that maybe later today. So right now there's the sample notebook, which has the placeholders and the code to take off and start working on project 2. And the project 2 document are there. And I realize you're studying for the exam, but some of you over the next 2 days might break away some time and say, this is going to be our team, this is who's going to do what, and that sort of thing. Because it's all part of your time management that I'm into, just like you are right now. It's very critical.
Is it the same rules for teams as last?
Yeah, it's 3. It's 3 like I had before. If it worked well for you before, don't change your recipe. But some of you people, I know a lot of people worked alone, and some people told me later they weren't planning on working alone, like you guys were going to work together, and neither of you did. Well, just, you know, do what you want to do. But the only rule I could change, and I did this last semester in DSP, as I said, a graduate student can work in a team of 2 if he or she agrees to work with an undergraduate. And I know that immediately 2 guys would probably jump on that, right?
Probably, yeah.
But that's a strange relationship, right? It doesn't happen that often that people that are good friends are in both classes. I don't know, I'm thinking about that. You'd probably take it though, right?
Yeah.
Is anybody else in here, would anybody else do that? Because usually graduate students like working alone because they don't associate with the undergraduates. I'll think about that. I mean, did you do yours alone last time?
Worked with him and Calvin, and worked out great. So
Okay.
that's fine too.
I'd say keep it like that.
That's easy.
So I don't know what else to say about that right now. I'll maybe think of it when I start looking at the project with you a little bit later. What I'd like to do is continue on to try to wrap up Appendix A. There's not really a whole lot more to it, but this is sort of the meat of Appendix A. And I'm happy to say at least one of the teams that's presenting this Friday, Jonathan's team, we just had a team meeting and I was reviewing their slides. They're using some of this material, a small piece of it, in their presentation on Friday. So comm systems engineers definitely use this stuff. But then we'll jump over to the project because not the project, but the exam, because as I posted last Friday when I got asked a little bit about the exam, I put this paragraph up here, getting ready for the exam. I want to get into that and give you as much detail as I can. I want to understand for myself what the boundaries are, because I just reviewed the old exam 1 to know where we left off, and that's kind of the big question there. Where did we leave off? So where do I pick up for this exam? And then where does exam 2 leave off, and what does it leave dangling out there for the final? So we'll be getting into that next. So I think where we left off, we had just come through Free's formulas, which, backing up, the whole idea, the culmination of this appendix is cascading subsystems that begin with some device. It might actually be an antenna connection, but some device, and then ends with delivery of the signal to a demodulator or some other aspect of a receiving system. So it can be any number of blocks, and they're abstracted in the labels here, block 1, block 2, but it might be an amplifier, a mixer, a filter, piece of feed line, bringing the signal from your antenna to the receiver front end, and so on. So the formulas are rather simple, but you have to work everything in ratios. You can't work in decibels. So when you're actually doing these calculations, and I cleared my deck, what I wrote last week, both of these formulas involve working with the ratios themselves, not the noise figure in dB, not the gain in dB, but actually the gain as a ratio. It's a power gain, and the noise figure as a ratio involving the specs on the device. And usually the specs are given in terms of dB, so one of the first things you have to do is convert everything to ratios. So before we actually do a couple of examples, and this part is not going to be on the exam, okay? This is new stuff for the final, but I'm just wanting to get through it. I will give you more examples in this area. I've got, there's not a quiz next week, but I think I've got 3 mock quizzes effectively for this topic, this last part of Appendix A. So I've got a bunch of practice problems that I will be able to give you to look at. And even if we don't have time to work on them in class, you'll have a chance to look at the solutions that I'll post up for them. So the first little item is just to take a very special case of an attenuator. What happens if we start our system off with the first block being an attenuator? So this attenuator is given as the letter L for loss. So when we talk about a system having gain, we would say it has plus 10 dB gain. If it's an attenuator, do we say it has a gain of minus 10 dB or a loss of 10 dB? Just, I'm not trying to make you say it's a yes or no question. It's just, it depends. If you want to call it a loss, though, it's going to be a positive value. If you want to call it a gain, that's going to be a negative value in dB. So the idea here is if you buy an attenuator, or I've got some sitting in my office, an attenuator will be usually cylindrical if it's a coaxial attenuator, and it will say on there 10 dB. So if the attenuator is stated as having a 10 dB attenuation, is that a loss of 10 dB or a gain. It's not a gain of 10 dB, right? So it's got to be a loss. I'm just trying to make sure the terminology is clear. So that's why in the, let's see, where did I set that? No. One of these days I'm going to talk to my friend. Give me some time. He never clears his stuff away before I'm wanting to go. At any rate, that's why in here the L is in the denominator though, because it's listed as a loss. So, question?
Just noticed that you mentioned it in dB. I always think of attenuator loss in dBm. Why would you choose to?
Okay, you can't say an attenuation is in dBm. The dBm gives you units of milliwatts, reference to milliwatts. So an attenuator doesn't have any units associated with it.
Doesn't care.
No. The dBm units come along when you're passing a signal of, say, plus 10 dBm into a 10 dB attenuator. What comes out the other side? 0 dBm, right? Yeah, be very careful with that, because that's one of the things about working these problems. And you're going to have two choices. You can work logarithmically when we're doing the link budget here in a few minutes, or you can work with ratios again. And I know from grading papers that probably about 50% of you will want to work with dB and just add and subtract rather than multiply and divide. The others of you are, I think, wary of it because you're afraid you're going to make a mistake. So you'll convert everything to ratios and you'll always multiply and divide for that reason. And then the units are more clear. But when you work with dB and dBm, then when you add and subtract, the units kind of seem nebulous because you have dBm and dB in the same equation and you're adding and subtracting. And it's like you scratch your head and say, how do I know what the units are, right? Does anybody else feel that way? Or maybe you haven't worked with it yet. When you're sitting there in the lab and you're doing measurements and putting attenuators and things in, that's when you start having to wrestle with it and come to grips with it. Actually, everything in engineering makes more sense when you actually have to do something, right? Sitting here in class doesn't really make it as real as when you actually have to deal with it in a real life system. At any rate, for the attenuator, if you drop into the model that we had for the equivalent noise temperature, which was this equation from last time, the power available at the output, the noise power available at the output is the gain of the device times Boltzmann's constant times the quantity that's the sum of the noise temperature of the input source, or the source temperature, and the equivalent temperature of the device that we're passing it through. So we add those two together, and we replace GA by 1 over L. Remember, we're working with ratios right now. So when you work this through, make the substitutions, you end up with this result from the algebra, working through the algebra. So you conclude then that the equivalent temperature, or the effect, let's see, I've got to make sure I'm saying this right. Is it equivalent or effective? Because I get the two of them confused. Yeah, effective noise temperature. The effective noise temperature is going to be this quantity, so when you work that around, 1 minus L quantity times Ts is T effective, and then when you solve for the noise figure from this, which is going through the algebra to convert back and forth between noise temperature and noise figure, remember this is the conversion. The big answer is that the noise figure associated with an attenuator is exactly the attenuation value. So if you had a 10 dB attenuator stuck on the input to a device under test, you would have made the effective, the noise figure associated with that attenuator is its attenuation value. And is noise figure good or bad? It's a measure of a system's noisiness, right? So the larger it is, the more noisy the system is. So one way of thinking about the attenuator and the noise figure idea is that if your signal comes in like this and you immediately attenuate the signal with the attenuator, the signal level goes down, but the noise is the thermal noise property. So the attenuator cannot attenuate the noise below the thermal noise level. So basically you bring your signal down and you bring it down closer to the noise floor as a result of going through the attenuator. Can't get around that fact. So in a practical setting, you generally don't want to do what this block diagram says. If you have a really weak signal coming in at the antenna and you've got to run it through a bunch of feed line that has attenuation, because RF cable has attenuation, it goes up as frequency goes up, you generally have to mitigate that somehow or another. And what's frequently done is to move the first amplification stage out to the antenna itself to avoid the feed line. That's what you see on most homes that have satellite TV, and some of you probably have that. Does anybody have a satellite dish for their TV? So you've got more than the antenna out there. You've actually got a preamp sitting out there, right, on the back of the dish. You probably don't have a separate power line now, because you have what they call phantom feed, where you actually send DC down the coax cable to run the electronics. And that's used in audio too. If you need to bias electric condenser microphone, you can send bias down the feed line to that from the preamp that sits at the end of the feed line in an audio application. But at any rate, that's why that's done. It's not always done, but the disadvantage is your electronics has to withstand the cold temperatures and sit outside and be weatherproof and all that other good stuff. But it's generally needed, especially on satellite dishes, because the antenna can't be too big for your home use, and the satellite can only produce so much power because it's running under battery power, except when the solar charges it. So we'll come back to that in these examples now. So the attenuator's attenuation value is equivalent to its noise figure. So this first example of working with Friese equations just breaks this system up into attenuator, RF amplifier, mixer, IF amplifier. So the specs in this example are given all in dB. The attenuator is 1.5 dB, so you would immediately be able to say the noise figure is 1.5 dB. That would not be given to you. You just have to make that assumption based on the knowledge that the noise figure of an attenuator is the same as its attenuation. Then you go ahead and take the rest of these numbers. So in order to work with the equations now, we can use either one of the approaches. We can work with this or this. So you just have to set yourself up to work with either approach, either get the effective temperature or the noise figure. And if you're going to go effective temperature route, this was the conversion equation. So, well, no, not this one. This is the conversion equation right here. So you just have to convert back and forth, and remember that T naught is 290 degrees Kelvin. And that's sort of another story that one of my professors told me a long time ago. If you were selling amplifiers, you could be deceptive and rate the noise figure in dB at a different temperature other than room temperature. That would be a deceptive way of selling an amplifier, right? Because then you could alter its, you could make it look better than it would be at room temperature by making it, speccing it in a different fashion. I just remember the teacher told us that, but nobody would do that, would they? In theory, they wouldn't do that, but advertising sometimes is deceptive. So the first thing I did here is I converted everything back to ratio. So on the left-hand side, I converted the gains from dB back to ratios. And remember, it's always 10 because we're working with power ratios. So when you take electronics, you use 20 log base 10 so much because you think that's the way decibel is defined, but actually decibel was defined as a power ratio, and it assumed the input and output impedances could be different. So when you were doing power calculations, it was always the output power over the input power, 10 log base 10 of that ratio. Electronics does a slang version of that because it says, okay, we're going to take the output voltage over the input voltage and assume that the impedance levels are the same, so we can cancel those impedances out, V squared over R to get power. And then you can take that 2 from the log of a V squared and bring it out front, and 10 becomes 20. So you should remember that, but it fades away after a while, right? Too much fun with the same thing, you forget that 20 was there as a 10 originally. At any rate, so you got to divide by 10 everywhere in here. And likewise, when you convert noise figure in dB back, I guess in one of these, well, why did I do that? F3 is 10. I'm not sure what I did here.
10 over 10 is
Oh yeah, okay. 10 to the 1. At any rate, so I've got all those numbers at my disposal, and then I just plug into Free's formula. So you plug in, for starters, what the noise figure is, and that's the 1.41 for the attenuator. That's its attenuation value. It's got a, you just have to go back up to the top here and plug in F1. So that was the first number that we got. F1 was 1.41, and then we plug in the gain of the first stage minus 1 divided by the product of G1 times G2. So that is going to be, or plug in G1, which is 1 over 1.41, and this is where that's the noise figure of the attenuator, but then this is where the second stage is really hitting you hard, because this second stage doesn't have a really good noise figure, and the fact that you're not getting to divide by the large gain that it might have if it was a preamp in front of this that had a low noise figure, this actually makes matters worse, right? Because this number is in the denominator, so it multiplies the numerator and adds a larger number onto the first term. And then eventually, when you get further into the cascade, you get a large gain that jumps in here, the gain of 100. And then this effectively takes this out of the equation. That 10 noise figure is kind of mitigated by the gain of the preceding stage. But here, you don't get to mitigate that because your first stage is essentially a number less than 1, being that it's an attenuator. But that comes out to a ratio then, and then you take 10 log base 10 of it. And then you got the noise figure in dB. If you want to convert it to noise temperature equivalent, you can just convert it back with the formula using room temperature 7.19, and then get it in degrees Kelvin. Or if you wanted to, you could work this entire example using the other version of Free's formula with equivalent temperatures. And I guess that would be I was thinking I did that in here, but I've got that in the other examples for the mock quizzes. You could actually just do that here if you wanted to. I'm not going to do it right now, but you could work the second equation, put in T equivalent everywhere. So then what you'd be doing there is you'd be running through the equations with T equivalent and you'd be doing this thing with it. So every place you need to get a TE1, TE2, and TE3, and so on, you're going to go down and use the equation I was using right in here to convert. So just take your F values, F1, F2, F3, and so on, and plug it in and get TE1, TE2, and then plug into the other form. And then you'll solve for the effective noise temperature of the cascade, and then you can convert that back to the noise figure, and it should work out the same to within some decimal places. My guess is, again, when I grade the finals, I will see that the majority will pick the noise figure approach. A handful of you will choose to do it with noise temperatures. Compared to the beginning of the semester and Fourier theory and everything else we did, how does this stack up in your mind? No comparison? Right? You should say, wow, this is almost like nothing compared to where we started. But how would you rather end the semester? Up against a brick wall where you got to look like that to climb it, or just look down and say, I'm fine. I'd like to coast to the finish line a little bit. So the next variation on this, and this could be the way a problem would be, is to do a swap up in here. So that's what this is saying. Let's interchange, put the preamp out at the antenna, and then redo the calculation. So now the attenuator comes second, the preamp is first, and now because you've got that huge gain of 100 first, when you come along to the second term, you can handle that attenuator much, much better. As a matter of fact, if that attenuator was even greater, suppose it was a piece of cable that was even longer, or maybe it was a matching network that was a lossy network that had 5 dB in it, you'd be able to manage it a lot better in terms of not being a big penalty to your system. The only thing we haven't done at this point, what we're going to do in the next example, is bring in the temperature of the antenna so we can get the noise power at the end of the cascade calculated. So here's another example that has an attenuator, and you're given a noise temperature at the antenna, like it's looking at a particular part of the sky, so it's getting some thermal effect of what's up in the sky. And now we're going to calculate the available noise power and the signal power. So we'll suppose that we're working in a bandwidth of 100 kilohertz. We're going to calculate what is the noise power available at the output of the cascade, and then what is going to be the signal power, assuming that all these gains get applied. So really all we need to do here is just go back to the previous calculation where we already had, since this is the exact same cascade, just go back to the previous calculation, make sure, since I didn't get a chance to study this. We just get to be able to use T effective and then bring in TS, bring up what the entire gain is of the cascade, and then just work this through. So the noise power available at the end of the cascade is going to be the gain all the way through, which is just the sum of the gains in dB. And then bring in our T effective. So we have to convert noise figure to T effective, and then we add to that the temperature of the source, bring in the bandwidth and Boltzmann's constant. So this is where we start splitting ways of doing problems. This is my preference, is to work in dB. So I will get the gain all the way through by just adding all the gains in dB. I will bring in and factor out KT0 as a known constant to me from my bizarre memory of never forgetting it when my professor said, don't ever forget this if you're a comm systems person, minus 174 dBm per hertz and T naught, being T90, makes that minus 174 dBm per hertz. So now this equation is the logarithmic version of the equation up at the top there. So when I break the equation at the top, I will go 10 log base 10 of all of this stuff, and I'm going to break apart the product into the sum. So I have log base 10 of this product, and it's going to be the sum of the gain in dB, and then K times T naught. I bring T naught in there so that I can get my minus 174 dBm per hertz. And then I just have to work with this ratio here of the temperatures, but it will still be a 10 log base 10. So when I put everything in parentheses like I've done at the end here, I'm going to be doing 10 log base 10 of all those quantities so that down below here I can add and subtract accordingly. So 86.5 is the gain. Minus 174 dBm per hertz was factored out, and then I have 10 log base 10, the ratio of the temperatures, and then I have 10 log base 10 of the bandwidth. And then here's the crucial factor. I'm doing adding and subtracting in dB. How am I going to get units out of this thing? This is where it's a little bit nebulous. I get units out from which term? Which and only term in here has units on it? That's the dBm per hertz, so that has units on it. The 86.5 is unitless. Log of a ratio of temperatures, unitless. Log of a bandwidth, what is the units associated with that? Hertz are with that, dB dash hertz, dB hertz. So the dB hertz cancels with the hertz in the denominator from that dBm per hertz, and we're left with dBm. If you don't like this or you want to do it another way, you can just go back to multiplying. And then you can see how the units will work out. Watts or milliwatts, and then milliwatts per hertz is what KT naught would be, unitless. Gain is unitless. That's got units of hertz. So it's got to be that the hertz cancel and you're left with watts or milliwatts. I have to leave you to your own devices on this in terms of which way you want to do this. Just practice at it, and I think you'll do fine. But this is where errors can creep in. Again, I like the log business better. I was actually taught that the reason why we work with decibels is because people are lazy. They don't want to multiply and divide. They just want to add and subtract. And if somebody makes up a budget, a linked budget, they generally do it in a spreadsheet, and they'll use Excel or something like that. And that way they can put all these components or subsystems in, and then they can just have the spreadsheet do simple math like addition and subtraction all the way through. Okay, so now the question that's asked is, what must the received signal power be at the antenna terminals for the subsystem, or for the system output SNR to be 20 dB? So that means we want to have the power at the end of the cascade be 20 dB above this value. So we add 20 onto that, and we're going to be minus 8.71 dBm. So I did that down here, and that's what this guy is right in here. And then if you bounce yourself from the output all the way back to the input, you have to take the gain off of the cascade, which is the 86.5, and now that's the input to your receiver to get a 20 dB signal to noise ratio in a 10 kilohertz bandwidth. And I guess this is kind of typical. And Jonathan, remember we were talking about this earlier, why in your system, in your link budget, it's so whacked. He's got a system. How many plus dBm is present?
25
And that's how many miles away from the site? Or kilometers? 1 kilometer? That's the radar system at Eglin. If you're in senior seminar, you've already seen this before, but this is more typical. You're going to be down in the minus 70s, 80s, and 90s dBm wise for your link budget. That's how much received signal power you'll expect at the terminals. Okay, now we're going to spice this up a little bit and throw in free space propagation channel. So we're going to suppose we have perhaps a relay link, just some free space propagation. So we have a ground station and an antenna, receive antenna. We'll just be working on one side of this, maybe the uplink or the downlink, but you can put them together if you want to. So basic radiation theory of propagating electromagnetic waves, which is what you have when you have time-varying sinusoidal electromagnetic waves. And this is the full Maxwell's equations, which gives these ideas where you have an E and an H wave that are orthogonal and they're propagating through space. So the ideal isotropic radiator to me is like a point source. You can think of it either back in basic fields theory as a charge in the electric field, or you can't do that for the magnetic field because you have to have a dipole, or you could just think of a point source of light that's illuminating with photons radiating out in all directions. So you have so much transmitted power going into this point source, and at a distance d, if it's radiating a spherical wave, what is going to happen to the flux density or the power density at a distance d? If it's radiating equally in all directions, what happens to that power? It gets painted on the inside of that sphere, so 1 watt becomes so many watts per watt. What's the unit going to be? Meters squared, right? It's going to be an area. And what's the area, the surface area of a sphere? Squared, right? So we take that total power and divide it by 4 pi d squared, and that's the power density in watts per meter squared. I got into this over the weekend because some of you know that we got the Field Foxes quite a few weeks ago, and I was finally allowed to take it home a second time because it had the asset tag put on it finally by the university. And my wife has been complaining about the microwave oven interfering with our Wi-Fi network. So I decided I need to learn how to use the Field Fox. I'll take it home and I'll see what's going on, and it can monitor channels, it can track channels, activity, and it can measure power in dBm. So sure enough, when the microwave is on, the channel that our wireless router has decided is best, because I have it in the mode where it automatically selects the Wi-Fi channel. Remember that homework problem or that quiz problem? We're sitting right on that exact frequency where the microwave is radiating and leaking things out of its box. So I messed around with it for a while, and then my wife was all worried, like, maybe our oven is broken, it's radiating too much microwave power. So I looked up what the standards were, and I need a magnetic loop antenna. I think I read in the Wikipedia that a microwave oven, if you're 2 inches from the gasket, where the door closes, the power level has to be less than 5 milliwatts per centimeter squared. So I need to get a calibrated loop, which I think we have in the Dr. Kelker's lab, and then hold that 2 inches from the gasket and just see if that's what I'm measuring. I think it's probably okay. It's just that it's definitely interfering with the Wi-Fi. So I split the bands up, so you can now choose either the 5 gigahertz or the 2.4 gigahertz, because it's a dual band router, which I'm guessing most of you have a dual band router, right? So that's temporarily making her happy. But she's still worried about the power level. It's kind of cool, though. You can use something that you're working with at school to help figure out a problem at home. That scores some points for sure.
Yeah, but normal house, the toolkit doesn't include a $10,000 fuel.
Field Fox, it's actually a $15,000 Field Fox, but because it does microwave network analysis too, and does this other scanning stuff. Take the comm lab next spring, and hopefully I'll have some labs written that'll have you outside making some measurements with it, because that's what I want to do. I want to get some reference antennas and be able to go outside and sit outside some of the buildings on the campus and just interrogate what the wireless is doing. Okay, so the next piece of activity, or next piece of information, is going from the isotropic radiator, which no antenna really is truly isotropic, radiates equally in all directions, to an antenna with directivity, which means directivity just means there's more power radiated in a particular direction, and that's described with power gain, GT. So you only put in so much total power, and that's that. If you're ever listening late at night to a radio station when they're doing their FCC requirements, they have to state so many times a day, broadcasting from a transmit antenna in such and such location with so many megawatts of effective radiated, effective isotropic radiated power, EIRP. You ever heard that before on a radio station? They have to, the law requires that they state that. So now we're going to take that and say, now we're going to take some of that power and we're going to focus it. We don't increase the power with the antenna gain, but what you do is you put more power in certain directions and less power in other directions, and that's the gain. So an aperture type antenna, such as a parabolic dish antenna, has effective aperture area that's going to be much greater than the wavelength squared, which is the operating, related to the operating frequency through the speed of light and the frequency, center frequency or the carrier frequency, has this relationship for a simple aperture antenna. It says that the gain is going to be 4 pi times AT over lambda squared. And if we assume that the receive antenna is also an aperture antenna, like two dishes, one on the transmit and one on the receive, it has area AR for the receiver, AT for the transmitter. It will have this exact same formula, so putting those together, we can create now a link budget. Typically what will happen is they'll put a fudge factor in, so a loss factor for extra system losses like attenuations in feed lines, other things that are just going to be swept up into a lump term would be L0. And so the aperture antenna is in here and here. And then we have to take into account the free space path loss. So just the fact that we're separating a transmitter from a receiver, again, we base that calculation on path loss, which comes about because of the divergence of the spherical wave. The wave front is just getting thinner and thinner. It's kind of like, why does a balloon explode when you fill it too full? The skin gets thinner and thinner as you stretch it out, and eventually it fails. So the RF energy that's painted on the inside of that sphere, as you diverge out, it gets a thinner and thinner coating of watts per meter squared. So that factor pulls out of these equations, or is factored in as the inverse square law, so lambda over 4 pi d squared. So you see the 1 over d squared is sitting inside of that now. So you put that up in dB, and you've got the received power is going to be, if you group these terms together, it's going to be 10 log base 10 of the received power in watts or milliwatts. And so you have how many terms in here if you want to break this down? 1, 2, 3, 4, 5 total terms. So 5 terms will sum, or 4 of the terms are additive and 1 of them is subtractive. So we put that down here. There's the 5 terms. 1, 2, 3, 4, and then 5. So this constitutes the link budget. And you would design the link budget based on what you want to have for signal to noise ratio at the output of the receiver. The calculation we already did, you would then incorporate this so you'd have the full setup. So we'll go through an example of that, and then I'll be done with this. Except for more examples that we'll look at next week when we start reviewing for the final. So here's a satellite comms example where there's an antenna on the transmitter that has an EIRP of 38 dBW, and the transmission frequency is 400 megahertz. This is right in the book, but it's eerily close to the radar problem that Jonathan's team is working on, right? It's kind of coincidental, I guess. So that combines together with the receiver specs, which are assuming that the temperature of the source and the effective temperature of the receiver cascade is 1,000 degrees Kelvin. This problem is very broad brushed, and it's not getting into the intimate details of the cascade and what devices. Is just saying overall this is what the noise temperature is effective of the receiver. Antenna gain of 0 dB, so that tells you it's an isotropic receive antenna, approximately so. Loss fudge factor of 3 dB, a bandwidth of 2 kilohertz, and a satellite that's in geostationary orbit, so it's 41,000 kilometers away. So all the numbers go in this fashion. That's lambda, right? C over F. And then you have 4 pi times the distance. The range is in the denominator, so that's the first term. You have the EIRP that encompasses the transmit's power and the antenna gain at the transmitter. You have 0 dB gain from the receive antenna, then you have your fudge factor L0, which is subtracting off 3 dB. Put those numbers together in decibel format and then do the additions and subtractions. You end up with minus 141.74 dBW, and then if you want to shift down to the more familiar for receiving type folks, dBm values, you add 30 dB onto dBW to get dBm because it's a smaller unit, so the number gets more positive. And so that's minus 111.74 dBm. What's the receiver output noise power going to be on this system? So we pull other information off of here. We're going to now use this value, the noise temperature, and we're going to use the bandwidth, and we're going to use the gain all the way through the system. And the gain all the way through the system is 0. There's no, the gain is 0 in this case. There's just going to be K T naught, and then that's factored out, so you can have TS plus TE over T naught, and then the bandwidth, and that comes out to minus 135.62 dBm. So overall, your signal to noise ratio is a positive value of 23 dB. I don't have another example in here. There is a little bit more exotic example, I think, in one of the homework problems I gave that involves a digital comm link. But what we're going to see in the project for digital comm is that if you're operating binary phase shift keying and you're looking for a particular signal to noise ratio at the demodulator, which would be at the end of this cascade, 10.52 dB will give you about 10 to the minus 6 bit error probability. And then it's a waterfall shape, so by the time you get up to 23 dB, the error probability is going to be very, very tiny. So the link is in fine shape if you were using a bandwidth of 2 kilohertz, which is pretty narrow. So you'd have, like, in BPSK, 2 kilohertz would give you a 1 kilobit per second data stream, which is pretty tiny. Make the bandwidth wider through this term right here, and then that number is going to get bigger. So you're going to let in more noise, and then your signal to noise ratio is going to drop down, and your link is going to start failing eventually because you've opened up the bandwidth. You can't send at that high a data rate. Does that make sense? More bandwidth, more bits per second, but more noise, because that's directly proportional to bandwidth in our equations. Everywhere in all of our noise equations, we've got B as the direct multiplication factor. Right over there. So what would you do if you wanted to send data at a higher data rate and you needed the wider bandwidth and you didn't want to change any components except maybe for antennas? What would your antennas end up having to do to compensate for the wider bandwidth and more noise that you'd let in?
A higher gain.
Higher gain. So you'd put a bigger antenna on a bigger dish. Adding more gain won't really help by itself, right? Because the gain is going to increase the signal, but it's also going to increase the noise proportionately. So that's not going to buy you anything. Lower noise figure would help, though, but bigger antennas would help. The other thing that would help tremendously is more power from the transmitter, or reduce the range. But if you're on a geostationary link, you can't change the range because you got to be 41,000 kilometers away from the satellite. What are you going to do in your house? Like my wife's situation with the Wi-Fi not working right, she was in the habit of, because the router is in our bedroom and the kitchen is where the microwave is, and she works in the living room frequently, sitting there watching TV and working on her iPad. What she would do is she would just stand up, walk to the back of the house into the bedroom where the router was, problem was solved. So the interfering source, which was degrading the ability of the link to function, was between her and the router, so just get on the other side of it and the problem was solved. But so two things were happening. Her receiver wasn't getting jammed as heavily by the microwave, but more importantly, she was also at a disadvantage because the signal wasn't as strong because of the attenuation through the walls and the hallways. As she walked closer to the router, she got a much stronger signal. The interference from the microwave oven was less because she was further away from it, but still, it was still present. I was seeing it all throughout the house as I was doing my measurements with the Field Fox, which I guess is kind of cool when you can walk around with your receiver and spectrum analyzer and see what's happening. Any questions on this basic example? Okay. 4 o'clock, 20 minutes. What do I want to do? I was going to talk a little bit about the project, but I also was going to look at Chapter 5 notes for a second. So what I have in these notes is not Chapter 5 from the book, but Chapter 5 from a wireless communications class that I taught quite a few years ago, and it just kind of overviews things at a high level, different types of modulation. and it actually starts with analog modulation, but then it gets in to digital modulation. So I'm going to just skip through a few pages here and get to the modulation type that the project is going to spend some time on. There's two parts to the project. The first part is pretty basic in characterizing PCM encoding and decoding and the effect of quantization noise on the recovered analog from the PCM decoder, and then on also the impact of the bit errors in the digital part of the link due to signal to noise ratio. So this reviews through standard linear analog modulation. It gets into binary phase shift keying, which is part of the project. Quadrophase shift keying is part of the project, or at least a whole family of modulations is part of the project. So the modulation, it also entails some pulse shaping ideas for spectral occupancy reduction and square root raised cosine. I'm just skimming along until I get to the more exotic modulation. So the more exotic modulation is based on quadrature multiplexing, which was at the end of chapter 4, and this was where you took information, put it on the cosine carrier, and independently could put information on the sine carrier. This is part of chapter 4, so it's part of the exam. So when you go to that type of modulation, you can get into, first off, the complex baseband representation, but you can look at modulation, say binary phase shift keying is very simply saying at the signal constellation standpoint, or what's called the signal space, you can say you send a 1 by sending information at 0 degrees phase that has an amplitude of square root of EB, where that's the energy per bit, or you could send a 0 at 180 degree phase shift, and that's on the other side on the real axis there, phi1. With quadrophase shift keying, you can use fully both in phase and quadrature, or cosine and sine carriers, so you can put your signal constellation points at these two possibilities on a circle. The only difference between these two is the orientation of the angles. This is probably the more common way of thinking of it, but the other way is also equally important. But then there's many other two-dimensional schemes. So there's M-ary phase shift keying, which the project does not look at. And then there's quadrature amplitude, and this is what the project looks at. And looks at this exact setup that's shown in this equation right here, where you have pulse shaping, and then you put bits up, multi-amplitude, not bits, but multi-amplitude values for the B's and the A's, and they take on values like that. And so 16 QAM allows you to put a combination of amplitude in the horizontal axis and amplitude in the vertical axes. So you get a square constellation typically. So the numbers that I have built into the code you'll explore are constellations that are 2 by 2, which is QPSK, so it has 4 points. So it's called M is equal to 4. M is equal to 16, which is this, which is 4 by 4. M is equal to 64, which is 8 by 8. And then M is equal to 9. M is equal to 16 by 16, which is 256 QAM. I don't think I have the denser modulation is not shown in here, but so that's what you're going to be playing with, is these denser modulation schemes, which end up encoding more bits per signal point in order to be very bandwidth efficient. And this is the heart and soul of three things that we all utilize quite regularly in our lives. We utilize LTE cellular, which uses QAM. We utilize Wi-Fi, which uses QAM. What's the next one? What's the remaining one that I'm thinking of?
SATCOM.
Well, SATCOM does too, but in our lives daily. Bluetooth, Bluetooth uses GMS or GFSK, but cable modems use it. And if you don't have a cable modem through Comcast, you've got DSL, digital subscriber loop or something from the telephone company that uses QAM too. So we're surrounded by it, and everybody's recognized the fact that more bits per second per hertz of bandwidth is what we thrive on, because we thrive on data. So I decided that would be something good to explore a little bit more of, just at a high level, to get introduced to some of the idiosyncrasies of it. Enough said about that for now. So I don't have a review sheet specifically for this exam. I will have that for the final though. But
And we're allowed to use our previous group sheet as well.
yep. So you can have your old two-sided sheet. A new two-sided sheet. The formulas pages. Probably don't care as much about the Fourier stuff, but it's still useful as you do about trig, because trig seems to have been more important in the more recent material. Also, the Bessel functions are on there, so you'll need that stuff. And it's 5 pages as before, with 1 to 2 problems per page. And you've got the 2 old exams to look at, so now we just have to nail down start point. So when I was looking at the old exam, I saw that the last problem on the first exam involved superheterodyne, a dual conversion receiver, which was essentially combined with a general topic called frequency translation in the book. So I'm going to move just beyond that, and I think it was interference was the next discussion, which was not a real rigorous discussion, but what I want to do is go look at the notes at this point so we can be clear on that. If that's okay by you, to be clear. So I'm going to jump back and look at chapter 3. And then we can step through what we'll be doing since that time. Okay, so here was an example of double conversion. This was kind of like what was the last problem on the exam. And then if I go beyond that, there was some discussion of mixers, which is a fascinating subject into itself. We spent a little bit of time talking about that, and I showed you some implementations. Somebody in here is working on mixers, right? I heard somebody talking with Dr. Song about mixers a couple of days ago. Isn't somebody in this class? Did I not hear the voice correctly? I thought it was one of you guys that was in our office last week talking about mixers.
Yeah, that was me.
Are you working on an independent study in mixers, or?
We're doing an amplifier independent study, but we were going through the Hozar microwave engineering budget.
Okay.
And our last section was mixes.
Okay.
Yeah.
Because I used to teach, well, I'm the one that developed the class for here, and I never got a chance to do much with mixers, but at any rate, so there's a lot of neat stuff out there. I'm not going to really ask any questions about it, except there could be some generic question on a mixer. I don't foresee that because I didn't have any like that on the old exam. But so the next topic we had after mixers was interference and linear modulation, and this is not a rigorous topic, but it had to do with if you're doing coherent demodulation or envelope detection, what was the impact of interference? And the main takeaway on that is if you're doing coherent demodulation, whether it be double sideband or single sideband, interference just linearly grows at the output of the modulator as the interference level increases. If you could eliminate the interference with a bandpass filter because it was outside of the band of interest for your receiving application, you'd be all well and fine. If you're using an envelope detector though, and that's useful for single sideband and AM, not for double sideband, then as the interference grows, you get to the point where initially the interference is like the coherent demodulator, it just linearly adds. But what we saw was when the interference, that was this case right here. Oops, I can't. Yeah, I should put it. Well, my pen decided to stop and start. So the bottom line was the message was lost. If the interference is so big it swamps everything out due to the nonlinear effect of the envelope detector. So that's about all we could say about this interference analysis for AM signals, for linear modulation, whether it be a coherent demodulator. It's all well and fine as long as you don't overload any component. You just get the interference gets more and more powerful, but with the envelope detector, it eventually gets to the point where it's lost. So if I was to ask a question on that, it would be a qualitative question, a short answer type of thing. Then we went into sampling theory, and what was important in sampling theory, I'm going to have to move fast here, was not the low-pass sampling theorem. I can certainly ask a question related to that, but the important thing that was new here was the bandpass sampling theorem. This is the summary of the low pass, but a few pages beyond that is the bandpass theorem. So that was this stuff here. You did a homework problem in it, and so I feel safe that I could ask a question like, here's the scenario, here's the signal. The signal occupies this spectral bandwidth. According to the low-pass sampling theorem, I'd have to sample at greater than this frequency. And if it was the bandpass sampling theorem, it's not a matter of being greater than a frequency. It's finding this exact frequency that will work. And beyond that, I can't ask a whole lot more because it gets more complicated. And I think I tried to make that clear by having you do that problem. Remember where I had the tool in MATLAB and you played around with things? To me, that's a very fascinating topic because it comes into software-defined radio ideas. But there's not a whole lot I can do. But I could ask a very simple question like, can you get by with a lower sampling rate if you go to the bandpass theorem? So you could say, check that out and see if it works. And that's about all I could do. Because I don't think you can do a whole lot without having the help of a computer, except the basics. Then we had analog pulse modulation, and the only pulse modulation that in the end I'm interested in for this class is PCM. And you're going to be playing with this in Project 2, but I think where PCM came into play was in the biggest way that this whole section at the end of this chapter comes into play. I mean, there's a lot of details that I'm spinning by here, but if I was to do any one thing on that, it would be related to the quiz Does anybody know what quiz that was? It was a mock quiz, I think, but I don't remember. I'm going to guess it's this one. There were 2 quizzes in here. See if it'll let me have a chance to look at them. Nope, this is the Wi-Fi one.
I thought it was like quiz 9.
Okay.
Closer.
It's got to be before this. Sorry, I didn't get. It's 8. Okay. It's got to be 8, right? We're spinning down our time, unfortunately. Yeah, this is it. This problem right here, problem number 2, this is the type of problem I would go for, something along these lines where it combines the idea that was the next topic in here, multiplexing, which I was mostly interested in digital multiplexing, not with the commutator and the mechanical thoughts, but in the idea that I would just multiplex things together, and I didn't have that in the notes, but we did talk about it, and that was the point of this problem right here. So you'd want to look at quiz 8 in this second problem, because this involves the use of sampling theory. The way the problem is set up in here, you have to figure out what's my lowest possible sampling rate, and then how many bits per sample, and then how many bits per second I have netted out of that. And then the multiplexing idea is bringing together different types of sources that are analog and digital, and then coming out with an overall bit rate. And then if you decide to put in some data framing, which you'd have to have, which would be some overhead in the digital signaling sense, then that.
But you basically just add all of your bit rates together.
Yeah, exactly. But to do this problem, you have to know a little bit about low-pass sampling theorem, and you have to think about PCM, how many bits per sample. It's a nice little easy problem. Easy in the sense that you just have to think clearly. Any problem is easy if you can think clearly, and that's the whole problem in life, seemingly, is can I think clearly at this moment in time? Has anybody ever struggled with that? I know I have. If you haven't had enough sleep, thinking clearly is always a problem, I think. Okay, so motoring on with the time that remains. So this was a true statement. Oops. All the things we covered in chapter 4, we didn't cover everything in the same level of detail, and I don't have the time remaining on that.
No Appendix A.
So this is up for vote. Do you want me to do anything from Appendix A, which would be like Boltzmann's formula?
Like the thermal noise? Would that
Yeah.
replace a question from chapter 4? Because if so, I'll vote for that.
It will. It would be, if I was to go from chapter 4, or Appendix A, dialing way back up in here. It would start off with the equivalent noise voltage, and so it would be a problem like this, and then it could possibly be Nyquist's formula, where you would have to use something like this. The only example problem that I worked from Nyquist's formula just was with the resistors only. I could possibly throw a capacitor in there or an inductor, but you would have to use that, and that's where I would stop.
Those were the ones on.
There were 2 problems at the end of set number 11, yeah. They just involved resistors. I'm willing to do that, but if you guys don't want Appendix A, I'll save it all for the final, in which case then you'll have all that on the final.
Keep in mind, those questions were easy. And
They're
you
very
replaced
easy.
Some of the difficult questions on this coming The final's gonna be whatever it is anyway. It's just, yeah, it's cumulative, so may as well take points when we can get them.
We're overtime right now, and I appreciate you all sitting here and not racing away, but do you want to have a vote or do you want me to decide? I'll decide right now and tell you what it is. Okay, who wants a tidbit of A? Raise your hand. Okay, that's the majority. Okay, that was my plan. That was my vote. So I got my way too.